Well, hello and welcome to this installment of the California Dreams Microelectronics Hub's Technical Seminar Series, where we highlight key technologies and advances being developed within our hub and beyond. My name is Mike Haney. I am the Deputy Director of the California Dreams Hub. Today, we're very lucky to have Chu-Chen Shui from the University of California at San Diego, where he is an assistant professor of electrical and computer engineering. He received his PhD from UCLA and then spent about 8 years at Intel as a research scientist and analog engineer. He's received multiple Intel Division Awards, but also awards such as the 2015 IEEE Journal of Solid State Circuits Best Paper Award, the 2020 NSF Career Award, and the 2022 UCSD Best Teacher Award. Today, his seminar is titled Energy and Bandwidth Efficient Silicon-Photonics Technologies for AI Accelerators, 5G, 6G MIMO Applications, and In-Package Integration. And I'm very excited to hear this talk, and I hope you are too. Chu-Chen, the stage is yours.
All right. Thank you, Mike. Yeah. Okay. Good afternoon, everyone. I'm going to start my talk, and let's see. Okay. So the outline here, I basically split my talk into two major categories. One is the we call it AI application, and the second part would be the 5G, 6G MIMO applications. And my talk actually contains three major components in these two different applications. Okay, so the first part we will focus on we call the monolithic photonic electronic accelerators. But this accelerator can be used for both the AI application or the this 5G, 6G MIMO applications. So let's quickly look at how we're going to apply those techniques in the applications as the motivation for developing this monolithic for photonic and electronic accelerators. Okay. So here's some detail in terms of how the development of today's AI applications. So one of the example is this what we call ChatGPT. I think everybody know that the ChatGPT is a very important, impressive large language model developed by OpenAI. Just within a few months, actually, the user is now at that point of time actually it's more than 100 million users, and today definitely is way much more. The problem here is that to support this ChatGPT, it's a huge amount of computation. It requires we call a lot of the matrix multiplication process. So here I'm showing a very basic example. Even though I don't think it's really necessary we understand all this the operation and the algorithm of this large language model, but I just want to show you that in this process, okay, usually this training and also the task execution process of this large language model, it requires for example, right here, I'm showing the input matrix is X. And it has the pre-trained Q, K, and the V, three different matrices. So sorry, WQ, WK, and WV. Okay, so it will create, based on the input matrix X, it will create a QKV, three different matrices. And then based on the Q and the K, they will create the input for what we call the softmax operation. Okay, so you can see we have this QK multiplication result. And if you plug those QKV into it, you will basically showing equivalent to the X times WC times X again. So it basically it's we call it double matrix multiplication. And then because we do the multiplication 2 times, right? And then we plug this QK into what we call a softmax transfer function. And then once we have this softmax transfer function, we will do the result is also a matrix. It times V. Again, it performs the double matrix multiplication. So this telling us that this entire process need to do a lot of this called we call a linear algebra or matrix multiplication, and the size of those matrices actually is super huge in terms of the number of user and the number of parameters that are used in this entire ChatGPT functionality. Okay. The second important application is what we call 5G, 6G channel, wireless channel estimation. So right here, we are not really doing wireless communication. We are not really focusing on the wireless part in this 5G, 6G. We are focusing on the computation part in this wireless system. Okay, so that's what we call the channel estimation, because today this 5G, 6G application, especially this what we call the extended reality experiments, it actually also require a lot of an antenna and receive a lot of information from all different user and all different antenna and find the estimation of the channel response. And that's what we call the channel estimation. Of course, people has been developed a whole lot of different approach to do this channel estimation. So I'm showing here a very simple example right here. People call this a Newman series. A matrix inversion approximation, because when they need to find out the channel response, they need to find the reverse of the matrix Z right here as the example. And the first, the equation right here kind of a little bit complicated, but you can treat the inverse of the Z, which is a ZK minus 1. It can be formed by the accumulation result of this DE and the D minus 1, those kind of matrix. And the matrix, D and E actually also coming from Z. Okay, but in any case, this Newman series approximation turns out will become the final equation I'm showing right here. This YK essentially represents as the inverse of the matrix Z, and the K represents how many times they do the iteration. So that's why YK is B plus A times YK minus 1. So it means YK minus 1 is the previous iteration result. The point right here is that again, I want to showing you that this YK, every time you want to get a YK, you actually doing the matrix multiplication between A and YK minus 1, and also do the what we call the matrix summation plus B. Okay, so again, this is showing you that, okay, if this matrix is super big, right, then this computation process requires certain amount of the we call it matrix multiplication, even though it just even though we are targeting at the matrix inversion, but in any case, once we use this kind of Newman series, the basic operation still whole lot of iteration and the operation of what we call a matrix multiplication in the basic linear algebra. Okay, so here's the kind of introduction in terms of the application and why we are doing this. We are doing this. We call a monolithic photonic electronic linear algebra accelerator. The goal is that we want to accelerate the process of doing all this matrix multiplication process. Okay. Then today, of course, the all the XPU, including CPU, GPU, and the multi-thread processor can do all of this kind of task. So I'm putting a table right here. That's what we call a digital computing. Okay. And then we are thinking out loud that, okay, if we can use photonic computing to do even better job, at least compared to the digital computing. So we kind of do a quick comparison right here. Okay, so the building block, of course, the photonic computing, we relying on both photonic device and electronic device, and later on we will show you the implementation we are doing. And the digital computing, no doubt, there's CMOS advanced process digital circuits. Okay, so in terms of signaling, how to do the computing, how we make those information do this multiplication together. Digital computing, of course, using digital signaling, and photonic computing here, we actually using analog computing. And I would say actually that's a downside right here. So we list a few items right here, highlight in red. Actually, because of this analog computing, such that in terms of accuracy, maintenance, noise immunity, signal conversion, hardware calibration, and the system integration, actually photonic computing doesn't really take too much advantage right here, because basically that's the why human beings since the 1950s start putting everything into digital domain. Okay. However, the hope we are looking at right now is actually start from the benefit of the photonics. The benefit of photonics is actually the first one is it has a very high, we call it signal connectivity. Easy way to think of this is like if you have a single wire for the digital or electrical signal, right? Each wire it can only carry one certain signal of information. But the photonic connection usually rely on what we call a waveguide. It can contain whole lots of independent, separate digital data information in a single connection. Okay, so that's why we call the capacity in terms of connectivity, the photonic computing is much higher. And the other thing is the loss. Okay, the optical loss in the silicon versus the electrical loss, especially this today's a high bandwidth and high speed application, electrical loss compared to the photonic optical loss in the silicon, digital circuit actually not really taking too much of advantage. And the third one right here, third one means my pointer highlighting right here is the energy consumption. Energy consumption, the photonic device, it almost consume negligible amount of power compared to the entire system. So the photonic computing later on, I will show you that the majority of power actually still coming from the electronic circuit supporting this photonic computing. Okay. And the end of the advantage we want to take is we call this process scalability. Today, Silicon-Photonic process technology, a lot of advanced foundry, they are developing this. They still have a lot of the potential to keep improving the Silicon-Photonic process technology. But the digital computing today, so far, I think everybody know that in terms of the situation of Moore's law, the process node the device gets smaller and smaller, but in terms of the bandwidth and the power efficiency and the power density, not necessarily we can get too much of benefit from the pure CMOS process technology. Okay. All right. So to introduce how we implement this, we call it matrix multiplication. We quickly back to the this kind of equation in terms of how we do the math. And then we're going to use hardware, either digital way or the photonic way. We basically want to implement using hardware, right, to do this mathematical operation, right? So here it shows a very simple example of the matrix y times a vector z right here. And of course, in terms of their dimension, turns out the outcome, we call the yz, is also a vector. Okay, this is just one example. But the keys right here is that to perform this multiplication between y and z, each element of the outcome, which is for example, yz1, okay, yz1, it's the dot product of the first row vector of the y times the z vector. Okay, so actually, I think this is not hard. Everybody know that. So the dot product essentially is each element of y, first row of y times all the element of z correspondingly, and then sum them together. That's why we call the dot product, and that's the first element of the outcome yz. And now the hardware, what we want to do, basically just realizing this dot product. Once we can realize the dot product between two vector, right, then we can do matrix vector, we can do matrix, we can do all these linear algebra operations. So the key is that how we implement this dot product operation. Okay. And more detail is that within each dot product operation, you have element times element, and then followed by we call the addition or summation operation, right? So you can see this YZ actually can be decomposed into four separate product and then summation, product and then summation, product and then summation, right? So each product and then followed by a summation we call a MAC. That's what we call a multiply accumulate computation. This accumulate actually, the name coming from, we have a multiple terms summed together, so it's like an accumulation. But essentially each MAC, it contain, you can treat as a single product and a single summation, okay? So this is that's the in terms of terminology. So for example, right here, you want to form the YZ1, you will need a 4 max. Okay, you will need the operation of 4 max. But if you need to form the entire YZ, right? You have the entire Y times the entire Z, then you have 16 of max operations. Okay, so once we have this understanding, we basically we want to do the element of Y and element of Z, they multiply together, and then once they each one of them multiply together, we sum them together, then we accomplish our job, right? That's what we want to do. And how can we use the photonic and associate with the help of the electronic circuit to implement this behavior and the functionality, right? So here's the one example right here. So there's a lot of detail, but I try to elaborate this within this talk. So you can see there's here I represent by 4 by 4 array right here. They basically represent as that matrix of Y. Okay, and the vector of Z, right? Vector of Z is one dimension vector. So essentially, we have this Z I highlight in black means they are still in the digital domain. So once they go through the we call it DAC, which converting the digital information to analog information, then that analog information, which is a voltage, you will control we call a micro ring modulator, such that they can encode the digital domain information into optical domain, represented by optical power. Okay, represented by optical power actually. So you can see here it's kind of small, but I'm trying to point out right here the Z in marked in black. That means they are digital information, and then they turns out after those entire array of the micro ring, they will be encoded into this colorful Z's, but they actually is represented by optical power. Okay, optical power of course, in the photonic domain. Okay, and those Z are in different color because we actually encode the Z into the power of different wavelengths. So you can see we have the laser com source to provide what that we call the WDM carrier, that they have different wavelengths as the carrier, and each carrier going to be encode the information of the Z1, Z2, and all the way to ZD. Okay. And later on, we will use what we call the WDM approach to implement the multiplication. But here, let's quickly look at the basic component we need to accomplish this job. Okay, so of course we need just photonic device cannot accomplish the job. We want to take the advantage of the photonics. Okay, but it still need to interface with reality of this all the device is electrical, right? So we need this we call it DAC again to convert the information into photonic domain. Okay, and we also have we call it EQDAC, but either high speed HAS or EQ or low power DAC, they are all DAC. So they basically their job is converting the digital information into analog information, and then they can control the ring such that they can encode the electrical information into the photonic domain. But once we do the computation in the photonic domain, we have to convert those photonic information back to digital information, right? So we need we call this a photodiode, and also we call it TIA, transimpedance amplifier, and the ADC, such that we can convert the entire information from the optical domain all the way back to digital domain, such that we can get our outcome. Okay, so this entire operation requires the cooperation of the entire electrical circuit and the photonic device. Okay, and this is something I didn't mention at the very beginning because I want to point out right here is that the the integration between the photonic and electronic device becomes super important to form this circuit, right? So we are using, we call it monolithic process technology offered by Global Foundry, that it contains in the single chip. Later on, we will look at the photo diphoto, but the single chip it contains both high-speed electronic CMOS and the photonic. So the figure right here basically ideally, we can almost put every single component right here into a single chip without relying on the heterogeneous integration between the photonic and electronic separate dies. Okay, so here I already mentioned right here. So this is more detail in terms of the inversion, that how we perform this, we call a dot product, right? So let me quickly go through this part. Again, we inject all different wavelengths, and each wavelength will encode by a different a ring modulator that they has been biased through the thermal control at that certain wavelength, such that they can encode the Z, which is digital information, to become the light power. So we have this Z1, Z2, all those things represent as a light power. Sorry about this summation. Actually, this summation not really happen until they reach the photodiode. But here I just say the total power. Still, it's all the power of all different wavelengths. Okay. And then we have another entire matrix of the micro ring. That's the we call it Y micro ring. Those Y micro ring also encode from the Y digital information, and such that they can do the second modulation on top of all of this Z1, Z2, all the way to ZD. Okay, so we can do two types of the modulation, such that equivalently it's like a multiplication of the two power element in the light domain. So for example, right here, right, original all the Z1 all to the ZD, they have identical power, but because they pass the first Y11 micro ring, so the red wavelength, now it has additional modulation factor of Y11. Okay, and the second dot product, second element to element product is also doing the same thing, but you have to go through the second micro ring at the lambda 2. Once once the entire information going through all the these horizontal rings, then all the wavelengths, it will be modulated twice. The first time it's encoding the Z, the second time it's multiplied by the corresponding modulation factor, what we call the gain, power gain from the Y. So equivalently, it behave like those, you can see right here, basically similar to the equation we just mentioned at the very beginning, that equivalently like the multiplication of all the elements. But if you recall, the dot product, we need to sum them together, right? So the summation actually is done by intensity detection of the photo detector, because the photo detector it has no idea in terms of the separate wavelengths. So even though each product is sitting on different wavelengths, but once they receive all these different light wavelengths, they will merge all their power together, so that we can accomplish what we call the dot product operation, because we need to multiply every single element and then accumulate all the element together to become what we call the dot product. Okay, so here's just a quick view, but maybe I just spend a few seconds right here. This is the high-speed DAC we use to get the encode information from the digital domain, and then have this what we call it in the high-speed voltage mode driver. It basically converts this digital information into different level of the analog voltage. So it basically do D to A. Okay, and those analog voltage will control the micro ring, such that will convert into two different level of power. So here's the the concept of that's how we call the WDM. WDM basically the concept is from the optical communication concept. It has all different carrier, like we mentioned, different lambda. So I use different color to represent it. Okay, but each one we can encode into different by let's say different Y, so that they can offer different amount of the transfer function gain for each different certain color that we can offer as the encoding or the what we call the multiplication. Okay, the bottom one, we will mention this one. This is what we call a rest track modulator. For now, we don't have to worry about it. To design those micro ring, right? To meet the our purpose of what we call a dot product. Actually there's a lot of requirement right here. Actually, for example, we need to keep all the resonant wavelengths apart from each other. Otherwise, we will create a crosstalk. Because the multiplication happen at each single wavelength. So this multiplication and the other multiplication should not affect with each other until they doing the summation at a photodiode. But during the modulation part, they should be independent. Okay, so the delta between all these resonant wavelengths should be considered. And also the FSR, the oscillator, it actually this notch behavior will periodic show up in the spectrum. So for example, this red guy, right? This red guy, you have a notch right here, but once uh, uh, going through the certain span of the wavelengths, it will show up the this notch again. So this is what we call the FSR. And every single ring have this kind of behavior. So we have to make sure that each channel of the lambda, they don't have any overlapping between each lambda and any other of lambda. So the period of this red guy represent as a total number, total bandwidth we can cover for all different lambda. If this is space FSR space is wider, then I can insert more different wavelengths, for example. Okay, so here kind of showing some comparison. Again, definitely pros and cons. For example, the first two row we insert 32 of wavelengths. Okay, but in that case, we may have to make the ring, the isolation space, which is what we call the delta lambda, smaller, because if the same FSR I want to put more, then the isolation bandwidth would be smaller. Okay, then that will create more crosstalk. Or we can make the overall FSR wider, but that require make the ring much smaller. Okay, the real ring much smaller then will affect by the resolution of this process technology as well as the random variation during the manufacturing process. Okay. Or if we want to compromise in terms of the spacing and also the size of the ring, then we have to reduce the number of the lambda. So for example, right here, if we use a 16, then we could have more space and a better size of the ring. But of course, we are losing half the amount of the lambda. More lambda, we can carry more information. All right. So once we have those basic concepts, this is just quickly showing the example that, okay, we can do matrix vector multiplication. Then how can we do the matrix multiplication, right? Basically, the matrix multiplication is just the either special extension or time domain extension of we call the matrix vector multiplication. As we're showing right here, we have multiple layer, right? So each layer right here doing matrix vector multiplication. So if we have a multiple layer such that we split the Z, right? Z is a matrix. Now we can split into several vector, operate as what we just mentioned before. Then as long as we combine all the layers operation, then we can perform what we call a matrix multiplication. Okay, so of course this plot is showing in terms of we have the multiple layer in terms of, let's say, on the chip, it's on the same surface, but we need to duplicate the hardware, or we can using time multiplexing, meaning each vector multiplication doing one time, and then the second vector doing the other time using the same hardware. So this is a trade-off between the what we call the area and the bandwidth. And we can do even more aggressively. We can do double matrix vector multiplication. What does it mean by double matrix multiplication? Is basically the equation we are showing right here. We have three elements three matrix or vector. They want to entirely tie together, but we can do this actually entirely within the we call it photonic domain. Again, the reason is that we want to make all the this heavy computation inside the photonic domain. More we can do in this way, we can save more power and have a higher bandwidth, because we can minimize the amount of the EO, electrical to optical, optical to electrical conversion process, like we mentioned, which is inevitable. But if we can minimize those kind of signal domain transition time, then we can get more benefit out of from this architecture. Okay. Okay, so that means to do this, that means we need we call it a rest track modulator, but I probably don't want to spend too much time right here. The key is that we need to do additional multiplication. That means we have to modulate all the lambda together. The way to do this, we need to use a rest track, as we're showing right here, the bottom one, that its FSR actually relatively small. So we can do, it can using the single hardware, but it can modulate all different color of the wavelengths. Okay, so as you can see here, the resonant cavity of the raster, which actually will be way bigger than micro ring for sure, because its FSR is much smaller. Okay, it's the inversely proportional to the spacing of the FSR. Okay. So by doing this, we really quickly see if we can really do the computation using this kind of photonic accelerator. So we quickly do the verification using the foundry offer PDK with all the circuit and photonic device. The gray curve right here showing the ideal value, and the blue one showing the our computation result. Of course, we have the error because this is the analog computing. Okay, but the key is that this error has to be smaller than our target plus minus LSB over 2 in terms of the accuracy requirement of this analog computing. Okay, so let me quickly show you the test chip so far we have right now. We have multiple test chip, but today I can only show you the almost the very first one we tap out in the GF, and then we do the measurement. So this one basically is doing the single MAC operation. So that's why we mentioned that you have one element times the other element, but in the photonic domain and also in high-speed computing, this high-speed photonic computing process. Okay, so the bottom right and the top right here basically showing the dye photo. The dye photo here, you can see that the dye directly attached on the top of the PCB. Okay, and all the electrical signal relying on of course, from the PCB and the bonding wire attached on the pad of the chip. But the photonic laser, which is the carrier we just mentioned, is coming from this vertical fiber, as you can see right here. So that means what? That means the entire die, right? It contains all the this photonic and electronic device we have and we need. We don't need to do any heterogeneous integration. It's just directly single die and have everything. Okay, so here quickly showing in terms of the response of the microring, its sensitivity. It's a function of both the thermal control and also the high-speed PN junction, reverse bias of the PN junction. So the left-hand side showing the sensitivity of the PN junction, which is much higher resolution. Uh, much higher resolution, but you can operate much a faster rate. The thermal control, you can move more FSR change in terms of 7.4 nanometer per volt. You can use to tune the operating point of our modulator. Okay. And here, let me quickly jump to the next page, and I try to explain the linearity. All this D to A to D, analog digital converging this process, we have to take care of what we call the linearity because the limitation of the analog signal in the device. Okay, so right here we quickly show you an example that when we convert a digital information in the horizontal axis to optical power, right? If we don't do anything that, for example, in this case, you will like a black curve, the black dots from the curve is that it's not a linear curve, meaning supposedly you want to do the linear algebra, you want to do the linear operation, but the the converging process already creates a certain amount of error. That's what we call nonlinearity right here. So we have this, we call a pre-distortion digital approach that to correct those black dot to become this hopping curve such that we can maintain the linearity as much as we can, as you can show as you can see right here. Okay. So then let me quickly show you the multiplication we using this optical signal, what we can do right now. The first example, we have the constant multiplicand Y11 and the high-speed multiplier Z1, they ties together. Okay, so you can see there's three different examples right here in terms of different value of Y11. But the Z1 itself has a high-speed data in two different level, and they multiply by Y11 the constant value, such that the overall I in terms of this analog optical power, it's a function of the multiplicand in terms of this constant gain, and the multiplier itself is like a pen to high-speed digital, so it varies from two different values. Okay. So this slide at the we can directly look at the right hand side plot. We basically overlapping all different possible relationship between these two multiplication that we have a constant value from all 10 different constant value times the high speed digital information, but they encode in the optical power as a Z1 and perform this multiplication. So this one can reach about 6.6 gigabit per second per Mac. Okay. Similar approach, but we enhance the resolution in the multiplier. So now the multiplier is not just the two different level of the from the two different level of digital information, it actually from four different level of different information. So that's why we can call it PAN4. Equivalent is 2-bit of the high-speed Z1. But again, you can multiply by constant value of the multiplicand YY a different value. Okay. So if you can see this slide again, we overlap all the possible result in terms of the 2-bit high-speed data times the about 2.6 constant value. So overall, you become about 12 gigabit per second per Mac computation. Okay, this is a computation, not communication. Okay, one more example. We make it even more complicated. Now, the high-speed data is PAN A. PAN A means you have 8 different labels, it's 3 bits. Okay, and you also ties a constant value of the multiplicand. Then you can perform here the computation become 13.5 gigabit per second per Mac. All right, so let me quickly summarize this first part of presentation. Here is that in terms of this photonic computing with this monolithic integration, the advantage we want to take is really the again, it's really the power efficiency we want to mention. So we directly jump to the column at the very end right here is showing that this kind of approach, right? Starting from your vector size up to 4 by 4, this monolithic silicon-photonic computing can have better power efficiency compared to this ASIC, which is a CMOS process technology from the digital computer, digital accelerator. Okay. And roughly, if we compare into 256 dimension of the vector, of course, this is estimation result. We haven't really reached to such a huge size, but to get the same reference point, at that point, our area computation density, which is the area efficiency, is about 3.5x better than the CMOS accelerator, and but the power efficiency is about 26x. Okay. However, of course, there's no free lunch. The primary downside of this monolithic photonic computing is the accuracy, which is a resolution we can maintain. So we roughly, in terms of the several examples I just showed you in terms of measurement result, roughly we can maintain about 3 to 5 bits, or roughly about 4 bits of the accuracy. Okay, but the digital computing, they basically can maintain well in terms of the data precision, up to 8 bits. This is the publication result from the Google Tensor process. Okay. So let me, I only have a few 15 minutes, so let me start talking about the second one. Okay. The second one, this one is also for the for the AI application, but the concept right here is now again, the whatever AI application its computing system becomes so huge. Okay, its AI workload today, it's exponentially growing. So how can the hardware wise, right? A traditional way in terms of our hardware, how can we maintain such super exponential growth of the AI workload? So the short-term the short-term vision right here is that we want to maintain all this what we call a computing system. For example, right here, CPU, GPU, or whatever memory, either HBM memory or all different kind of memory, right? Today, commercial foundry, a commercial company, they can offer. We want to maintain this, but we want to improve the integration of all those components. So that's why we kind of propose this kind of panel scale reconfigurable photonic interconnects, meaning it's like a packaging, but instead of using traditional silicon interposer, we have this photonic interposer sitting at the very bottom, as you can see right here, used to perform the integration and the interconnection between all these commercial chiplets. Okay. So here quickly show you the cross section of the concept. The cross section of concept here is those gray area or black area represent as all whatever commercial product today people already have, either XPU, HBM, all those things. We want to maintain whatever commercial product they already have. However, the communication between all those chiplets, we want to perform using we call a photonic chiplet. This photonic chiplet was sitting right below this 3D integration approach is sitting right below the electronic IC or chiplet and perform two different major purposes. One is the communication, high-speed communication. We're using the optical domain, optical communication. But the EIC is all this commercial chiplets, not just the data communication. They need a lot of power supply. They need a BIOS. They need a low speed configuration. All those kind of things. They still need to maintain certain amount of the electrical connectivity and interconnection. So this piece of the PIC it offer actually both. Okay, it become the interface of those high speed and the high bandwidth, high computation bandwidth, each EIC or chiplet between this internal system and the external outside of this entire computing system. And here's the top view of the we call the PIC embedded glass interposer. Well, what we are thinking right now is that PIC is the yellow part. It's more like play as the tray sitting below those EIC. So this gray box is more like a EIC sitting above it. Okay, and then EIC going through the information going through this yellow box and then do all the communication. And how can we make this like as large as like a panel scale? The approach is that we can use the glass substrate, which those more like a display panel, because those thing is not dominated by the wafer size. Those thing actually is pure packaging level um, technology. So the size of that blue guy, the size of the bottom blue guy actually can be as large as the display panel. And the chip part, which is the yellow part with the photonic chip, or the gray box is the electrical chiplet. They using this 3D integration today already pretty popular doing this way to form the entire system. And the key of all the interconnection between any single chiplet inside of this system, high-speed part is formed by we call optical communication. For example, you can see those colorful crossbar channel. They are all used for the high-speed communication. Okay. And the other version is, of course, if in the future we can make this photonic layer together with the huge glass substrate, then we can further improve the idea into a single wafer scale integration, meaning we don't really need to separate the glass substrate and this we call the photonic IC anymore. The photonic layer directly can be fabricated on the glass substrate. And in this way, then the integration efficiency will be even higher because now the EIC directly talk with each other through the this wafer scale interposer. Okay. In any case, here this one quickly showing you the interface between the EIC and our photonic chip. Basically, we are using today's 3D flip chip integration and this high-speed interconnection between electrical signal and the optical domain, which have the modulator, the channel selector, and the photodiode between the photonic layer and the electrical layer to do the high-speed interconnection. And the last important item I want to mention in this technique is the crossbar switch technique. The crossbar switch technique is relying on this what we call the airdrop micro ring resonator concept to perform the crossbar of the photonic signal. For the electrical signal, it's pretty easy. We have different layers of metals. They can route all different way, but the photonic is not like that way. So, and also photonic, even the same waveguide, you want to do the 90-degree route, it also pretty tough in terms of its area efficiency. So how can we do crossbar? Basically, for example, right here, I'm showing the blue waveguide and a blue waveguide and the green waveguide. We relying on this airdrop coupling. We add an additional ring between these two layers. Of course, the assumption right here is we have 3 layers of the waveguide technology. Okay, so in terms of the coupling, the blue one can go through the orange one, which is a ring, then couple the information to the ring. Okay, so that means what? That means any information coming into this crossing node between the blue and the green, we can rely on those ring to turn the direction or bypass the information through this crossing node. Okay. So finally, okay, this one is more like an extension of the idea we just mentioned. This one is we actually can use the racetrack we just mentioned before, because the racetrack, it allowed to modulate all different wavelengths. Meaning, if I want to turn the direction of the light propagation, right? Because every single waveguide, we can have multiple different wavelengths carrier. So if we want to turn the direction of all the wavelengths together, then we need to use what we call the racetrack, because the racetrack, it have all the FSR. It can align with the carrier frequency, carrier wavelengths, such that it can turn the direction for all different wavelengths together. Okay, so the last, the final slide, a few slides, I want to mention the key of the contribution right here. So we quickly do the comparison between today we call the secant interposer at your left-hand side. And the right-hand side is what we just mentioned in using the crossbar switch as well as this photonic interconnection to form the interposer, to form the interconnects between the electrical chiplets. Okay, so here we try to unify the comparison between the left and the right, which we have the same size of the XPU and the same amount of the HBM, and almost the same area of this, what we call a unit interposer area, 62 millimeter times 57 millimeter. Under those kind of almost a unified identical condition, and we can see the performance between the two. Okay, so here's the final slide. I quickly summarize the comparison between these two cases. Again, the map to the left and right. One is today's silicon interposer. The right one is the photonic interposer we are proposing now. So they have the blue part, the blue number. Means they almost have identical amount of microbump usage, almost identical amount of the power efficiency for the data links, and bandwidth density for the data links, and the power density for the data links. Under those almost comparable numbers, the connectivity, the number of the waveguide in this case, right? The photonic only need 26, but the transmission line interconnection of the electrical signal need 736. Okay, and the total data bandwidth per XPU, communication bandwidth, okay, not the computing bandwidth, it's the 2x in the photonic interposer. Also, more importantly, by spending almost the same amount of power efficiency, the photonic interconnect, it can go beyond 500 millimeter compared to today, this a silicon interposer, it pretty much can only support 50 millimeter in terms of this communication interconnect distance. All right. So I think I should stop here. I will let the audience ask question, or yeah.
Uh, Thank you, Chuten. Very
Mm-hmm.
nice talk. Appreciate that.
Mm-hmm.
This seminar is now open for questions. I'm looking at the Q&A box and I don't see any. Oh, here we come. Here comes some. Here's a question. How temperature impacts the error rates? I suppose that applies to both
Mm-hmm.
concepts. Yeah.
Yeah. Let me quickly. The bit array here you care about, it's the major bit array. The temperature right here mainly affecting the performance of the rings and all those photonic device. Those photonic devices indeed very sensitive in terms of the the temperature. So in this measurement, right, we have very good control in terms of our instrument, in terms of the all this the temperature control. So at this moment of time, I don't have the good number telling you that okay, if we change it how much degree, then how much BR rate going to decrease. But this is definitely something we need to investigate.
Okay, let's see here. I have a question or two
Mhm.
myself. You mentioned that you taped out that your first chip at Global and the Global platform, Global Foundries.
Mhm.
I'm curious about um, how many wavelengths, about the state of the art of that. How many wavelengths were used and able to be used in that platform? Did you have to tweak any of the PDK elements, or would you have to if you go to a larger number of wavelengths?
Oh, okay. So I think this we can separate into two different questions right now. So from the global foundry standpoint, this process technology mainly support O-band. Okay.
Okay.
But so the O-band actually is quite large. Depends on the wavelength spacing we want to offer. So your question is actually more related to the COM source generation.
Mhm.
The console generation so far commercial, we can see the best one, I mean commercial on the shelf, okay, is probably 16 uh, different wavelengths as the COM source.
Mhm.
So if we have that COM source, of course, in this case, we don't have such so many wavelengths, but yeah, but that probably not really related to this global foundry process technology. So the
Okay.
COM source itself basically is external. That's what I would say.
Got, no, I understand. Very good.
Yeah.
Thank you.
Hmm.
Um, on the interposer, a
Hmm.
question I had is you mentioned that a picojoule per bit, approximate
Hmm.
cost per bit, but
Hmm.
it would seem that you could in principle get much better than that. So maybe if you could identify where
Yeah.
the loss mechanisms are, and maybe that's where the improvement can come as well.
Okay, so energy per bit, right? Here, you can see the electrical data. By the way, this energy per bit is the energy efficiency of the data link, not the processor itself. Okay,
Right.
used to communicate the data. Okay, so uh, the silicon interposer, right? Their I/O actually has to be split into all different standard because it has been developed for a long time. For example, here it contains we call it HBM5 and the UCIe5, and also we call it XSR5.
Mhm.
Three
Mhm.
different files. So all different files require different amount of power efficiency. So that number basically is the average result.
I
Okay.
see.
Okay, but the photonic side, we kind of use unified I/O. Regardless of distance, we can use the same amount of I/O. So that one is for all the photonic I/O. This 1.17 we estimate, but the number actually pretty close. The reason is that the today, right? Today the optical data links, even though the photonic side kind of have lower power, but the driver it needs a larger swing. For example, the case we're showing, it actually need to like a 0 to 2.4 volt, and also we need to inject the laser power. We also need to include the thermal control. Okay,
Right.
so the link power doesn't really show a whole lot of benefit in terms of energy efficiency. But actually, that's a good thing for the comparison because if you can see that under the almost same amount of energy efficiency, the distance of the interconnect that photonic can support is almost the 10x.
Yeah.
So in other words, if you want to support same amount of distance, then the silicon interposer will need much way higher power. You can treat
Understood.
like that way.
I understand. Thank you.
Mhm.
I've got time for one more question. I'll take
Mhm.
one from the audience here. I'll read it.
Okay.
At what scale of the photonic computing module will it become useful for practical application? 4 by 4, 16 by 16.
Mm.
That's the question.
That's a good question. So to be practical, right?
Mhm.
Uh, look at the sorry. Uh, if we look at this table, we intentionally compare with the commercial product from the Google TPU. By default, their size is actually 256 times 256. Okay, so if you are asking what's the reality requirement, I would say companies they won't do something useless. So I would say this 256 pretty much is the basic requirement they need to. Otherwise, they won't do this. Okay, but for us to implement this photonic computing all the way to 256 times 256, still have a certain amount of distance, a long way to go. Uh, I don't have good prediction, but we will make an effort from that.
But matrix operations can be broken down into pieces, right, and then recombined later,
Oh,
right? So,
right. So we can make a smaller one and have a lot of smaller one to become a bigger one.
yeah,
Yeah.
very good.
Mhm.
Very good. Well, thank you. If you
All right.
I think it's a very good seminar. I really
Mhm.
appreciate it.
Mhm.
And I will point out to the audience that we have an upcoming workforce development event, our next one, coming up soon in Arlington. So we hope to see you there if it works for you. Um, Also, Amy, if you go to the next slide, we have some upcoming seminars. We won't have one next week because of the holiday weekend, but there you can see that there are some coming up, and please check them out, and hope to see you here again. And with that, we'll wrap up with a virtual applause for Professor Strutt, and thanks everybody for joining. Have a
Yeah.
great
Thank you,
weekend.
everyone.